Hi, my name is Alexander Dillens from edevis, and today you are here in the test lab for optical Lockin Thermography. It's a powerful non-destructive testing tool to inspect, for instance, carbon fiber structures. You see here a test sample which is used for illustration today. So it's a flat plate, and on the rear side we do have flat bottom holes. These are simulators of flaws of defects at the material inner structure. How to reveal these flaws in the material? So if we just use the infrared camera and measure the surface temperature, we would not see inside. We just would see the same as with our bare eyes. What we do is an intensity modulation to produce a modulated heat wave into the material. By doing so, we obtain a good property of this modulated heat wave because the diffusion of the heat is linked to the frequency of the modulation. So if we have a quickly modulated light with a higher frequency, the diffusion length is small. We don't see very deep into the material. If we go to a much lower frequency, we can see further into the material, so we can see deeper lying flaws or defects. That's a very useful property. You will see that later on. Now, okay, let's start with the measurement. Let's position our devices properly. The first thing we should do is position the camera. We should see the entire sample, not more and not less. Next, we need to focus the camera. A very helpful utility is an aluminum adhesive, which is brought to the surface of the sample. Now we have a very good contrast in the infrared live video, and it's very easy to precisely adjust the focus position of the camera. Okay, that's fine so far. The camera is nicely positioned. Now the next thing is the lamps. We should bring the lamp into the right distance. For carbon fiber, 1 meter to 2 meters is okay. The nearer we are, the more inhomogeneous the illumination is. The more far away, the more homogeneous, but lower heating strengths. So we need kind of a good condition for that. And we need to care for the right angle between lamp and camera. There should not light being directly reflected from the lamp to the camera. This can bring us distortions in the images. First of all, we can set up the coordinate system. Normally we have a pixel coordinate system, but for the further evaluation, it would be very convenient to get a metric system with millimeter scaling. So what we need here is to bring in an optical target into the scenery, use certain patterns, Aruko patterns, and now we are able to do an automatic coordinate system calibration. As you can see, even with this very little illumination, the pattern was recognized and the coordinate system now is rectified. Now we can remove this pattern, this target, and we now see the sample with its metric scaling. You see here in the picture, that's millimeters now. Next, we need to set up the camera. The windowing and frame rate is less important for the optical Lockin thermography measurements. We will max it. What's important is the integration time or measurement range. We should select a measurement range which is appropriate to the heating of the material during the measurement. If the material is getting too warm, the sensor will saturate, so please select the measurement range according to the temperature development during the acquisition. Very often a range between 0 and 50 degrees should be appropriate for the Lockin thermography. The excitation device settings, we will select the halogen lamps and a sinusoidal heating, that's okay. For the recording, it's a good idea not to record the whole video. It will consume a lot of hard disk. we should rather select the evaluation where we just store the login results, the phase and amplitude information. Next very important parameter is the login frequency. This is directly linked to the diffusion length. So the diffusion length mu in terms of formula is square root of 2 alpha, the diffusivity, over omega, the circular frequency. The circular frequency is the frequency we select here. So by doing so, we directly affect the diffusion length of our measurement. For carbon fiber, it had turned out that frequencies between 0.5 Hz and 10 mHz are good if we have material thickness of roughly 3 mm. Other parameters you can see is the conditioning periods. That's important to allow the material to heat up a bit before the acquisition starts. That's necessary to obtain reproducible measurements. Usually a conditioning time of 10 seconds is appropriate. Next parameter is the acquisition periods and amplitude. Both affects the signal to noise ratio. The amplitude is the more powerful quantity, but it's limited by the lamp power and the capability of the material to bear temperatures. The acquisition periods are also good. If we increase them, the noise will be reduced, but of course the measurement time will be longer then. Now let's start the measurement. You can see the intensity modulation of the lamps. And after a short time, we receive the first phase image at 0.5 Hz, where you see no flaw. Why? Because the diffusion length was insufficient. We did not reach the 1 mm where these flat bottom holes are positioned. At 0.2 Hz, you now can see that we already see the first row of flat bottom holes. So we reached the 1 mm penetration depth. And at 0.1 mm, you see already the second row. So that's exactly what we can expect from theory. We practically proved that. Let's go into the measurement results now. We can select between amplitude and phase image. Amplitude is the relative temperature increase during the modulation of the lamp. As you can see here, in the amplitude, we do not see very well defects, but we could see if the intensity of the lamp is homogeneous enough. So this is more a measure of the quality of our measurement, not so much the indication of the flaws. Selecting the phase, we have different conditions. The background of the material is very homogeneous, and we have a very good contrast between flaw and sound material. In the bottom area of the measurement result, you see the frequency slider, and here we can step by step go deeper and deeper into the material by going to lower frequencies. The dynamics of the phase image you can see here is between -180° and 180°, but not all the range has relevant information, so we need to adjust brightness and contrast of the picture. Normally we do that by using the histogram function, so it automatically takes the effective range where there are realistic values, or we can adjust this scaling manually by using the mouse, as you can see here. You should not overshoot to see too much details. An average contrast normally is the best. In summary, you saw that Lockin Thermography is a powerful inspection method for carbon fiber inspections. Equipment used today was the edevis EDECAM microbolometer camera, our OTBIS system and DisplayImage 7 software. You saw how to set up the camera and system, how to perform a measurement, and the first step to evaluate. Hopefully you find this video informative. Thank you for watching. See you next time.